Hello my dear friends, welcome to my YouTube channel. In this video, I will talk about FinFET structure. In this presentation, I will discuss the following topic. First one, what is FinFET? Second, what is DevEdit? Next, how to write a program in DevEdit. This presentation is totally focused on how to write a program in DevEdit. To write a program in DevEdit, you must know about goal and purpose of creating a new mesh, defining region and their parameter, mesh creation, generic parameter, meshing in Z-plane, how to save the file in DevEdit and its syntax, difference between Silvaco standard and DevEdit, and the last one, silicon FinFET device in 3D with BQP model. To draw the 3D structure of FinFET, you must know about the DevEdit, how to write a program in DevEdit. Let's start. What is FinFET? A FinFET is a multi-stage device, a MOSFET semiconductor device built on a substrate where the gate is placed on 2, 3 or 4 sides of the channel or wrapped around the channel, forming a double gate structure. These devices have been given the generic name FinFET because the source drain region forms fin on the silicon surface. This is the structure of the FinFET, this is the length of fin, and this is the width of fin from this point to this point. The FinFET device have significantly faster switching time and higher current density than planar CMOS structure. FinFET is a type of non-planar transistor or 3D transistor. It is the basis for modern nanoelectronic semiconductor device fabrication. Microchip utilizing FinFET gate first became commercialized in the first half of the 2010 and become the dominant gate length design at 40 nanometer, 10 nanometer and 7 nanometer in process nodes. To draw the 3D structure of FinFET, you must write FinFET code in DevEdit. DevEdit is a device structure editor. It can be used to generate a new mesh on an existing structure and can be used to create or modify a device. These devices can be used by 2D and 3D simulators. DevEdit can be used as a simulator under deck build or through a graphical user interface. A limitation of device simulators prior to DevEdit was inadequate or poor structure meshes. A mesh containing too many obtuse triangles or any insufficient number of triangles may provide an inaccurate result or no result at all. A mesh containing too many triangles can result in excessive simulator processing time. Since the time most simulators grows geometrically with the number of triangles, it is critical to keep the number of triangles down to a reasonable number. DevEdit resolves these problems by allowing structures to be created or read into DevEdit in the form of Silvaco standard structure files. The mesh contained in the file can then be replaced using the mesh build algorithm. You can refine the mesh by setting parameters that describe critical area or by simply pointing to the area where fine mesh is required. Before DevEdit, we cannot remeshing a device structure between process simulation and device test simulations. When to use DevEdit? Defining a device interactively on the screen for subsequent device or process simulations. Second point, remeshing a device structure between process simulation and device test simulations, where the process simulator does not create a good grid for the device simulator. Remeshing a device structure during a process or device simulation when the mesh is no longer adequate for the next simulation step. The benefit of using DevEdit is that we can remeshing a device structure during process simulations. If you found that there is some problem in the meshing, you can change the meshing during the process simulations. When not to use DevEdit, you should not use DevEdit to perform the following operations: replacing numerical process simulations where accuracy is required, meshing 1D device structures. We cannot use DevEdit in 1D device structures. Startup. You can start DevEdit one of the two modes, 2D and 3D. For 2D mode, type DevEdit. For 3D mode, type DevEdit 3D. If the device is 2D structure, you don't write 2D. If the device is 3D structure, you have to write DevEdit 3D. To start DevEdit in a graphical user interface mode, use one of the following command for a Unix prompt: DevEdit and this start DevEdit with no active device. DevEdit fred.str and this start DevEdit with the Silvaco standard structure fred.str loaded. DevEdit fred.de and this start DevEdit with the command file fred.de loaded. DevEdit 3D and this start DevEdit in 3D mode with no active device. DevEdit 3D fred 3d.de and this starts DevEdit with 3D command file. The name of the file is fred.de, that is loaded. DevEdit does not currently support loading 3D structure files. Difference between Silvaco standard versus DevEdit. A Silvaco standard structure file and a DevEdit file is differ. A Silvaco standard file contains some information about each region, a mesh describing the device, and a list of impurity at each point. In the Silvaco standard file, first we have defined meshing, after that region with the material, doping and electrode statement. You can also define the impurity at each point. This file type must be used to pass the structure to a simulator. A DevEdit file contains the DevEdit cards needed to be created device, the analytical impurities functions, mesh creation cards, and DevEdit mode setting. Tutorial of DevEdit. This tutorial discusses aspects of mesh creation in DevEdit. It begins by discussing the goal of an efficient mesh for the device simulation. There are two examples. The first example demonstrates how to create a structure. The second example illustrates how to create a mesh in an existing structure. These two examples illustrate basic uses of DevEdit. If you want to write a code in DevEdit, you must know goal and purpose of creating a new mesh. I will discuss every point of how to write a code in DevEdit in code also. First point is goal and purpose of creating a new mesh. Specifying a good mesh is a crucial issue in device simulation. There is a trade-off between the requirement of accuracy and the numerical efficiency. Accuracy requires a fine mesh that resolves the structure in solutions. Numerical efficiency is greater when fewer points are used. If you are increasing the grid point, this will increase the simulation time of the code also. This will reduce the numerical efficiency. If you are using the less grid point, then the accuracy of the result is very less. Typical area that require fine mesh includes high electric field at the drain channel junction in MOSFETs, the transfer electric field beneath the MOSFET gate, area of high impact ionization around heterojunctions. Create a new structure. To start DevEdit, enter DevEdit and in a terminal window. This starts DevEdit in a graphical user interface mode, that is opposed to the batch mode. First you have to define the work area. DevEdit starts with the work area that uses a default setting. To change the size of the work area, change the depth and length, minimum and maximum value can be used to desired point. Syntax of the work area. Work area, x1 point, x2 point, y1 point and y2 point. Left point, right, top and bottom point, point 1 and point 2. Description. Set the viewing area seen in the main window of DevEdit X Windows mode only. X1 is the minimum X value of dry area, X2 is the maximum value of dry area, Y1 is the minimum Y value of dry area, Y2 is the maximum value of dry area. The work area will decide the length, width and height of the device. For setting this, you have to mention depth of the device and length of the device. Minimum value as a maximum value. Y value show the depth of the device and X value will show the length of the device. After defining the mesh, you must have to define the regions also. Adding a region. How to add a region in the DevEdit? Creating a device begins with adding regions. Each region consists of one material. Although an area of a single material can consist of more than one region, DevEdit allows you to create geometrical shape by typing the coordinate of the region. Second point, regions are made of a material and contain a list of non-intersecting polygons. A region can be made of several discrete polygons. If one polygon is contained in another polygon, it is considered a hole in the containing polygon. If a polygon is inside a whole polygon, it describes a region with material a hole in the hole. I will discuss about how to assign the polygon vector in the code also. For display purpose, a region can contain a color and a fill pattern also. With the help of generic parameter, I will define the color of the region and a fill pattern of the region also. This is only used when DevEdit open an X display window. Next point, a region can also be an electrode region. In that case, the electrode ID number can be supplied or one can be chosen by DevEdit. For future enhancement to simulators, a work function can also be applied to the region also. Next, region parameters. How to define these region parameters, in which I have to define the material of the region. Specifies what material the region is made of. Either it will be silicon, aluminum, gallium arsenide and etc. See generic parameters for a more complete description. How to define the generic parameter? You can define the color of the material also. Color used to display region during DevEdit in X Windows mode. This is an RGB bitmap with 8 bits per color. DevEdit has only a limited subset of these colors. Therefore, the closest match is used. Some basic colors can be specified by the name, such as red, green, blue, yellow, cyan, magenta, black and white. See generic parameter for a more complete description. Next, pattern. Used as fill pattern for display region in DevEdit in X window mode. See generic parameters for a more complete description. I will discuss about how to define the color and the pattern in the next slides also. Points. 2D point list. Used for the location of points making polygons that describe the region. The area of the region cover the work area defined by the polygon vector. Next, electrode ID. Electrode ID describe the region as an electrode. Setting the electrode number start from the 1. If region number 1 is not supplied, the lowest unused electrode ID number will be used. Next, work function. Used only if electrode ID is set to define work function for materials. This is not currently being used by any simulators, but may be used in the future release. In the resin part, next we have to assign the material and uniform doping. After entering the color of the resin, the material and the doping need to be entered. Next one, setting mole fraction. If you are using the aluminum gallium arsenide or any hetero material, you have to define the composite fraction for ternary and quaternary materials are defined in the atlas. If you are using any material that is not defined in the atlas, you have to define a new material in the code. Next, assign the polygon. Enter a polygon beginning at 0, 0. Continue to choose the point 0.001, 0. Next point x1, x2, x3, x4 and x4 by 4. That will decide the area of a region in the work area. Next, in the region, you have to define the electrode. The last region to add are the electrode. In only the boundary of the electrode contacting the semiconductor is considered. Here the height of the electrode and the mesh inside the electrode are of little consequence in atlas. The width of these electrodes does not matter in the atlas. Next, how to define the generic parameter in color format. The color can be set using a standard 24-bit number with 8-bit for each color component, red, green and blue. The easiest way to use this to use hexadecimal values by starting the number with 0x. Each component then has a range from 00 to FF. 00 means no color and FF means full color. For example, for the black is 0x 6 times 0 and the red is 0x FF and up to the white for 0x 6 times F. See the example below. Color this one will represent the full red, color this one will represent the full green and the color with this hexadecimal code is represent the full blue. Next is the how to fill pattern in the region with the help of generic parameter. On black and white displays, pattern filled are used instead of color. There are 18 patterns numbered 0 to 17, pattern 0 for solid and pattern 17 for empty are normally not used. Pattern 17 empty are normally not used. Each material has a default pattern which will be used by the region if no pattern is set. If you are using the default pattern, it will set the region with a different filled pattern. Next is how to create mesh in the DevEdit. Mesh build. First point, you can build mesh by base mesh, the geometry and impurities and mesh constraints, and create a mesh using a mesh parameter available option. The default parameters create a mesh advocate to define the geometry of the device. How to define the mesh parameters? Base mesh height and width may be used to create more symmetrical meshes for some devices. For most devices, setting mesh constraint provide the same results and also allow more fine tuning. Mesh constraints. This is very important to define a mesh in the DevEdit. The mesh constraints section is the principal area for controlling mesh construction. In this section, you can control the maximum triangle ratio, the maximum and minimum height and width, either throughout the device, or selectivity in the given region in a material type or underneath the region or material. Begin with selecting semiconductor region in the material type. Set the value of maximum height and maximum width. These values are valid for the mesh creation in all semiconductor regions. As mentioned previously, the mesh in the insulator and electrode are unimportant. If you don't define the meshing for the insulator and the electrode, that does not affect the device performance. We strongly recommend that each material layer or region have several mesh layers. You can define the number of mesh layer for one particular region. You can also adjust parameters for other layers. It is recommended in this example to increase the mesh density in the semiconductor layers so that several mesh layers exist in each region. Simply to increase the mesh density, you have to increase number of mesh layers in one region. How to define the mesh constraint in the DevEdit code? Syntax: you have to write constraint.mesh global. You have to define the region ID, region name, material, material type, and their dimension x1, y1, x2, y2. And you can also define the under dot region, under dot material, under dot gate depth, or you can use the default value of these parameters under dot region, under dot material, and under dot gate depth. You have to define the maximum angle, maximum ratio, maximum adjacent, maximum height, maximum width, minimum height, and the minimum width of the region, particular region. Description: mesh constraints are used to determine the size and shape of triangles during the meshing phase. The constraints are arranged in a hierarchy: global constraint, material type constraint, and the region specific constraint. To determine the active constraint in a region, DevEdit starts with the global value. The global constraints have predetermined default values. As the new region are added, the region initially default to the material type constraint associated with the region material. Once a value has been set, it can be restored to default to the more general level by using a parameter with no value. For example, maximum angle 100 can later be cleared by using the maximum angle has no value. All values of the current constraint can be cleared by using the default parameter. Next, how to define the mesh constraint parameter in the DevEdit code. Next, first one is the global. Set global constraint. The global constraint is also if region and material type are not used. Next, you have to define the region number. Specify which region these constraints apply to. Several region parameters can be set at the same time. Region name. Specify which regions these constraints apply to. Several region parameters can be set at the same time. Material type. Specify what material type these constraints apply to. Value can be a semiconductor, metal, insulator, and others. x1, x2, y1, y2. The four corners of a rectangular area to which the following constraint will apply. Next, depth. Depth. How deep in the rectangle should we form the surface of the semiconductor region? This parameter must be used in conjunction with under dot region, under dot material, or under dot gate statement. Default. Before setting specified values, reset all the values in the specified region, material type, or global constraint to their default value. By typing the default, you can reset all the values. Maximum dot angle. Maximum angle a triangle can contain. Maximum angle has a range between 19 and 180 degrees. Normally, points are limited by the mesh dot build to 12 connections. If the maximum angle is set to be 180, the connections limit is removed. In no case will be an angle actually to be 180 degrees. Maximum ratio of a triangle height to its width. Height upon width. Maximum height of a triangle in micron. Maximum width of a triangle in micron. Minimum height. Triangle shorter than this are not shortened during the impurity refinement. Minimum width. Triangle narrower than this are not narrowed during impurity refinement. For understanding about these commands, you have to go for the DevEdit manual. Z-plane. Define Z-plane in 3D mode only. Syntax: Z-plane, spacing, maximum spacing, and the maximum ratio. Description: Z-planes are created at the front and the back of all regions and at the specified Z locations. Additional Z-planes are added to meet the requirement of spacing, maximum dot spacing, and the maximum dot ratio. Parameters. Spacing. The spacing around the specified Z-plane will be restricted to the specified spacing. Spacing 0 means there are no restrictions specified to this Z-plane. Dot meshing 0 is the default case. Maximum spacing. This is the maximum gap in micron between the two adjacent Z-planes. Maximum dot ratio. This is the maximum ratio of the gap between the two adjacent Z-planes and the gap of the next Z-plane. Next, saving the file. You can and should save the file in two formats: the structure file and the command file. The structure file is a format used by other Silvaco programs, including Tonyplot and Atlas. Therefore, it is necessary to save the structure file for continued device simulation. The command file is a list of the instructions used by the DevEdit to create the structure and the mesh. To make additional change at the later time, save a command file so that the original set of DevEdit instructions can be read. Structure file. By convention, Silvaco structure file and with the extension .str, choose a name and use the extension. For example, example1.str. Save structure outf command is used to save the structure file. Outf command is simply used to save the structure file. You can now use the file in Atlas and Tonyplot also. Command file. It is good practice to use the same file name as the structure file but ending with the conventional .de extension. De extension is used to save the file in the command file. Therefore, in this case, it would be example1.de. Batch mode. You can also run DevEdit in batch mode within deck build without using the graphic user interface mode used above. Although you can directly input the command statements to create a structure and mesh. This method is more difficult than using DevEdit in graphical user interface mode. Using the DevEdit in batch mode, you cannot call the structure by using the Atlas command. So that we are using the graphical user interface mode to call the structure in the Atlas command. How to use the syntax of saving the file? Structure outf, the name of the file. After type master, it is the default if you want to write. Save file name, the name of the file, and the type card.desc, it is also default and the master you can use. Parameter file.name, file outf can be used to save the file. File name used as to store a Silvaco standard structure file or a DevEdit command file. The structure card only stores Silvaco standard files. Type of the file to store possible value are master, structure, card.dec. Silvaco, first one, master is the Silvaco standard file. .str also show the Silvaco standard structure file. Card.dec shows DevEdit command file. 3D parameter, type 3D mode. Next is the code we will discuss in the next slide. Silicon FinFET device in 3-dimensional with BQP model. This example demonstrates application of the BQP model coupled with energy balance to a complex 3D device. Application of BQP in the case of 2D quantization. The structure is showing like 3D, but the quantization is actually in 2D mode. Effect of quantum confinement on carrier density in FinFET we will discuss. This example illustrates the modeling of FinFET device using BQP and energy balance in 3D. The quantization inside the channel is almost two-dimensional, and since we do not have a principal direction of quantization, we cannot be sure that the model is calibrated until we do a calibration against a 2D Schrödinger Gaussian model. This is not currently available in Atlas, but a calibration performed for Silvaco by the author of the BQP model suggests using isotropic effective mass of silicon is 0.7 with BQP model alpha 0.3 and BQP model N gamma is 1.4. The 3D device structure is created in DevEdit 3D and the required model are set. After the solve.initial statement, the solution of a gate voltage of 0.2 volts is obtained using the no current initial guess parameter. A drain bias is applied and then the gate voltage is ramped to turn the device on. The drain current is plotted in Tonyplot and the device structure in Tonyplot 3D. The cut plane facility of the Tonyplot 3D can be used to look at the electron density and quantum potential in the channel, which illustrates the reduced electron density at the Si-SiO2 interface. By using the cut plane model facility of the Tonyplot 3D, you can find out the electron density, surface potential and electric field of the proposed device. Let's go to the code. Now the code starts with Go DevEdit in place of Go Atlas. DevEdit is used to define a device interactively on the screen for process simulations. Remeshing is possible in DevEdit between process simulations. You can start DevEdit one of two mode, 2D and 3D. In this example, I am using 3D mode so that I have write 3D. There is a difference between Silvaco standard file and DevEdit file. In the case of Silvaco standard file, a meshing describes the device and after that a region is defined with material. In case of DevEdit, a DevEdit file contains the DevEdit cards needed to create a device, the analytical impurity functions, mesh creation and DevEdit mode settings. To start DevEdit, enter Go DevEdit in the terminal window. This starts DevEdit in the graphical user interface mode. This will oppose to the batch mode. First, we have to define work area. This is the work area. DevEdit starts with the work area that uses a default setting. To change the size of the work area, change the depth and length. Minimum and maximum can be set to the desired value with the help of x1, y1, x2, y2 parameter. After the work area, you have to define the region statement. Creating a device begins with adding regions. Each region consists of one material, although an area of a single material can consist of more than one region. DevEdit allows you to create geometrical shapes by typing the coordinate of the region. Next, start with the region number 1 and the material is silicon. The regions are made of a material and contain a list of non-intersecting polygons. A regions can be made of several discrete polygons. For display purpose, a region can contain a color and fill pattern. This is only used when DevEdit open an display window. A region can also be an electrode also. In that case, electrode ID number can be supplied or one can be chosen by the DevEdit. For future enhancement to simulator, a work function can also be supplied. Generic color and pattern I have defined in the code. Generic parameter color. The color can be set by using the standard 24-bit number with 8-bit for each color component. I have already told you about that. The easiest way to use this is the use of hexadecimal values. By starting the number with the 0x, each component has a range value from 00 no color to FF full color. Next, generic parameter fill pattern. On black and white displays, pattern fills are used in study of colors. There are 18 patterns number from 0 to 17. Pattern 0 for solid and pattern 17 for empty. After the reason statement, mesh creation is to be defined. You can build mesh by base mesh, the geometry and impurities, and mesh constraints, and create a mesh using the mesh parameter available option. Mesh parameter. Base mesh height and width may be used to create more symmetrical meshes for some device. Mesh constraint. Start with the command constr.mesh. This mesh constraint section is the principal area for controlling mesh construction. In this section, you can control the maximum triangle ratio, maximum and minimum height and width, either throughout the device or selectivity in given region in material type. Mesh constraints are used to determine the size and shape of the triangle during the meshing phase. The constraints are arranged in hierarchy: global constraint, material type constraint, and the region specific constraint. So I have defined the default value. This is the global constraint with the maximum height 0.01 and the maximum width is 0.02. Next, the same procedure is applied for the region 2 with material silicon dioxide with their color and the pattern with the help of their polygon vector. Next, constraint command is applied to the region 2 by the default command. Maximum height is reduced to 0.001 and the maximum width is 0.001. Next, we are using the another region number 3 with the gate material, that is polysilicon, with the help of electrode ID 1 and their work function is 0. Polysilicon we are using with their color and the pattern with their dimensions also with the help of polygon vector. Now the constraint command is applying to the region 3 with the default and the maximum height and the maximum width. Next, region number 4. Having the material silicon dioxide with their color and the pattern with the polygon vector, constraint command is applying to the region 4. Then the region number 5 is drain and the metal is aluminum with the electrode ID is 2 and the work function is 0. We are using the aluminum directly with their color and the pattern vector with their dimensions and the polygon vector. Constraint meshing applied to the region number 5. Next, the region number 6 is the last region, that is source, that is the aluminum metal with the electrode ID is number 3 now and the work function is 0 with their geometrical parameter color and the pattern also with their dimensions and the polygon vector. Next, region number 6 is the last region and the constraint command is applied to the region number 6 with the default maximum height and the maximum width. Next, you have to define the meshing parameter. Base mesh height is 0.01 and the width is 0.005. Next, bound dot condition is applied with the maximum slope of 20, maximum ratio 300, RND dot unit is 0.0001, line dot straightening 1, align point when automatic. Next, the constraint command is applied with the maximum angle 90, maximum ratio 300, maximum height 10,000, maximum width 10,000, minimum height 0.0001 and the minimum width is 0.0001. Then the constraint command is applied to the semiconductor, insulator, metal and other also. Next, the constraint command is applied to the region 1 with the maximum height and with the maximum width. Now the constraint command is applying to all the region from 1 to 6 with default command and the maximum height and the maximum width. Next, constraint meshing is applied to the ID1, x1, y1, x2, y2 with their default and the maximum height and the maximum width. I have already explained about that in the PPT, so that you have to define these parameters very carefully. If you please note down the every point in the code very carefully. If you note down the every point very carefully, you can run this code in your laptop and you will get the same result as I got. How to choose this maximum height and the maximum width? You have to must know the length, width and thickness of the device. And the last one is the mesh.mod is the mesh build. Please note down very carefully. First I had applied the constraint command to the region. After that I had applied the constraint command to the different material, semiconductor, insulator, metal and other. After that I had applied the constraint command in every region number 1 to region number 6. After that I had applied the constraint command in the electrode ID from 1 to 5. Next is the mesh mode, is mesh build. Next is the Z plane. Define Z plane for 3D mode only. Z planes are created at the front and the back of all regions and at the specified Z location. You can save the file in two formats, structure file and the command file. The structure file is a format used by the Silvaco program including Tonyplot and Atlas. Silvaco structure file and with the extension .str. Choose any name and use the extension .str. Command file. It is a good practice to use the same file name as structure file but ending with the conventional .de extension. If you are designing the device in 3D format, you must define the Z plane. I have defined the Z plane from 0 to 0.100 micron with the equal spacing from that is equal to 0.1. After that I have saved the structure file using the command outf with the file name is quantmax.str. Next I have start the MOSFET calculation with the BQP model. Now the Atlas code is start with the command go atlas. I have set the parameter of BQP and gamma and alpha. Gamma is equal to 1.4 and alpha is 0.3. Next is the electrode name, doping, material. Please note down the code very carefully, point by point. Electrode name is bulk bottom. Doping number 1, P-type, uniform concentration 1E18. Doping number 1, Gaussian. N-type concentration 1E20. 1, Y minimum, Y maximum, Z minimum, Z maximum. Z later character because you are using the Gaussian doping. Then the doping number 1, Gaussian. We are applying the Gaussian doping, the same doping we are using for the different region. Next I have defined the material name. I have defined the silicon with their parameter, default parameter. You can change this value by changing the electron band gap, e.g. 300, electron affinity, permittivity, mass value and the density of electrons and with the command NC. Next I have defined the material oxide. Next I have defined the material polysilicon. You can use the default value or either you can choose the different value for this material. Next is the contact name. Gate work function is 4.85. We are using the model Fermi BQPN SRH Fermi BQP dot n gamma is value is equal to 1.4 and the BQP n alpha is value is equal to 0.3. Method maximum trap and block by using the BICGST and the dB limit 1.0. Next is the solve initial. Solve V gate 0.2 no current. This example describing the modeling of a FinFET device using BQP and energy balance in 3D. The quantization inside the channel is almost two-dimensional. The 3D device structure is created in DevEdit 3D and the required model are set. After the solve initial statement, the solution of a gate voltage is 0.2 volt is obtained using the no current initial guess parameter. We are assuming that the no current is flow at less than 0.2 volt when the VGS is equal to 0.2 volt. The threshold voltage must be greater than the 0.2 volt. A drain bias is applied and then the gate voltage is ramped to turn the device on. The cut plane facility of the Tony plot is used to look the electron density and the quantum potential in the channel. Next, I have applied the drain voltage from 0.001 to 0.01 volt with a step size of 0.0005. Save the log file and the gate voltage is applied to turn the device on from 0.2 volt to 1 volt with the step size 0.05 volt. Log F. Next, the output management connection command is used to find out the different parameter potential electric field from the structure file. Next, save the structure file. Tony plot command is used to display the structure file as well as log file. Next, last is the WIT. If you run the program, you will get the two files. One is the structure file and one is the log file. This is the log file. This is the linear current. I have changed into log format. The off current at the 0.2 volt is 10 raised to power minus 14 and the on current has value greater than 10 raised to power minus 6. We are assuming that there will be no current will flow less than 0.2 volt. I have start the code with the 0.2 volt. That's why the current is start from the this is the V gate less than 0.2 no current. I have run this code by deciding the gate voltage 0.4 no current, in which we are assuming that the threshold voltage is greater than 0.4 volt. I will show that result also. This is the result when we assume that the less than 0.4 there will be no current to flow, in which we are assuming that the threshold voltage is greater than 0.4 volt. But in this example we have taken 0.2 volt gate voltage having no current, and after that we are ramped the gate voltage from 0.2 to 1 volt. This is the result. This is the structure file. I have defined the work area x direction 0 to 0.02 and the z direction from 0 to 0.1. X direction is minus 0.01 to 0.02 and the y direction is 0 from 0.04. I have defined everything in the work area. This is the structure file. By using the cut plane, you can find out the potential energy band diagram from the structure file. This is the fin of the gate structure. This is the FinFET structure. This is the fin. This is the width of the fin from this point to this point, and the length of the fin is from this point to this point. My dear friend, this is end for today. If you like my video, please like, subscribe and share my channel. Thanks for watching. Thanks a lot.